So chapter 5 here is where we're at. We finished up naming last time. So in this chapter, we're going to talk about everybody's favorite stuff, grams to moles. We'll talk about Avogadro's number, and we'll finally get into officially empirical formulas and molecular formulas and how to do all those things. So let's get started with atomic masses. So atomic masses, which, as we've talked about a little bit along the way, is what you do see on the periodic table. It is the bottom number here that we do see when we look on the periodic table. And obviously, the atomic mass is the mass of that particular atom. It is related to pretty much all the particles that make up an atom, like our protons, electrons, and neutrons. But obviously, atoms are extremely small, as we know, so you can't really just like pick one up and pop it on a scale or anything like that to get the mass of it. So oftentimes in chemistry, when we can't sort of directly measure something, what's usually will happen is they will pick something to use as sort of a standard to compare everybody else to. And atomic masses is no difference. They actually used a isotope of carbon as the standard to basically compare everybody else to, and that is the carbon-12 isotope. And the carbon-12 isotope was used as sort of the standard for atomic mass. And the carbon-12 isotope has a mass of exactly 12.00 AMU. And AMU is a unit, obviously, of atomic mass. It is what pretty much it stands for, the atomic mass unit. And technically speaking, when you do go to the periodic table, for example, and you do pull off that number on the bottom, like what we find with hydrogen, that basically is there are 1.008 AMU per atom here of hydrogen. And that is sort of the atomic mass units used off the periodic table. We will talk about shortly in this chapter a more usable unit and a more common unit that's used from those numbers, which, as we will see in a bit here, is the molar mass, which is grams per mole. And that is obviously a much more convenient unit because it has grams in it, which is what we measure things on balances in and stuff like that. But AMU per atom is another sort of set of units that you can pull off from each of the elements that are there, and that would represent its atomic mass. An AMU is also called a Dalton, if you can find in a really old book. Somebody uses that terminology still. But one AMU is exactly 1/12 the mass of carbon-12 atom. So what they essentially did was they sort of compared sort of the magnitude of every other element to the carbon-12 isotope. And they, for example, for hydrogen, found that on average, hydrogen is about 8.4% as big as the carbon-12 isotope. So basically, they do like a little calculation, 8.4% converted into a decimal, move it over 2 places to the left, or divide by 100, times it by the carbon-12 standard, gives us, again, that number that we see there on the periodic table of 1.008 AMU. Similar type of calculations have been done for things like oxygen, which is 16 AMU per atom, iron, which is 55.85. Now, we can actually calculate the atomic mass of an element through a calculation. But again, we can see all these atomic masses. They're also sometimes referred to as atomic weight of each of the elements present there on the periodic table. Now, when we look at something, for example, like carbon on the periodic table, we actually do see this number, 12.01. My one blends in there, so let me change colors maybe. There you go, 12.01. Not sure if that's any better. But we do see this number 12.01, and you may say to yourself, if the carbon-12 isotope is a standard and it has a mass of 12 AMU, why do we see 12.01 there on the periodic table? And the answer is what we actually see on the periodic table is average atomic masses, and they're the average atomic masses of all the naturally occurring isotopes for that particular element. So, for example, carbon has the carbon 12 isotope and the carbon 13 isotope as its sort of naturally occurring isotopes. So this is how we actually can calculate the atomic mass of a particular element. We could calculate the atomic mass in AMU by taking the percent abundance, and that's sometimes called the relative abundance of the first isotope, naturally occurring isotope of that element, and we multiply it by the atomic mass of that isotope first. And then what we do is we actually add it. So people always want to multiply with this one, but we actually add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And it does depend obviously on how many isotopes you have, but you basically just continue this pattern. If you have 3 isotopes, you continue to do it. The percent relative abundance is basically the percentage of time that these naturally occurring isotopes appear. Um, Obviously, it's a percentage, so it should add up to 100% or in that ballpark if you have all the naturally occurring isotopes. So if you come across a problem where you add up the percentages and you're short from 100, that must mean that you're missing an isotope somewhere along the way, and you should have some information to allow you to figure out what that missing sort of isotope is. Now, when we look at something like carbon, like I said before, it has two sort of isotopes. So one isotope is the carbon 12 isotope, which has a mass of 12.00, and the carbon 13 isotope, which has a mass, as you can see there, about 13.00335 AMU. The carbon 12 isotope occurs about 99% of the time, and the carbon 13 is about 1% of the time. And that is what I was talking about earlier. These are their kind of percent abundance that they occur, those sort of percentages. So we could do our formula. We would take the carbon 12 percentage, convert it into a decimal, and again, you can either move the decimal place or divide by 100. We're going to times it by the carbon 12 atomic mass. We will then take our 1.1%, which is that guy converted into a decimal, times the atomic mass of our carbon 13. And that gives us, again, the number that we do see on the periodic table, which is our 12.01. So it is important to keep in mind that although people don't usually call them average atomic masses and stuff like that, you will probably never find a carbon atom that has a mass of 12.01. You would either find a carbon that is basically the carbon 12 isotope that has a mass of 12, or you would find the carbon 13 isotope that has a mass of 13 and some change. So, again, there's sort of average values of all these naturally occurring isotopes for these particular elements. Any questions on that? So again, a relationship, as you can see, between atomic mass unit and grams is this. So there is 1.66 times 10 to the minus 24 grams in 1 AMU. And again, as we will talk about, we do sort of use more molar mass, as we'll talk about a little later on, because again, grams are pretty much a common unit in terms of weighing things out. And that's obviously much better than trying to figure out how many AMUs things are and then has to kind of convert it into grams. So we could do some type of conversion factors. If we have we want to know the mass in AMU of 431 atoms of carbon, we could pull that information off the periodic table and use it really as a conversion factor. So that's 12.01 AMU in an atom. Or we could flip it around and put the atoms up on top and 12.01 AMU on the bottom. So dimensional analysis here, opposites cancel, atoms on top, atoms on the bottom, they cancel. leaves me with my AMU. We're going to multiply what's on top. Anything on the bottom would get divided. That will give us something like 5176 AMU would be the mass of about 431 carbon atoms. We could do similar type of calculations for everybody on the periodic table. There's aluminum. And again, when we look at aluminum, we will see that 2698 listed. And again, that would mean that there are 26.98 AMU per atom. Or again, you could flip it around and use it as a conversion factor in the other direction, 26.98 AMU. And again, our atoms here will cancel, leaving us our AMU of 2024. I will say that very rarely probably will you use AMU in terms of units there from the periodic table and calculations. More so you're going to use it in grams. And again, that's a more sort of usable unit for us. How do they figure out, for example, the percentages of these naturally occurring isotopes or their mass? They can perform an experiment known as mass spectrometry, or mass spec for short. And basically, they send atoms or molecules and they're ionized, so they're heated up, they break apart, and they're accelerated down a tube. And within that tube is sort of an electrical field and a magnetic field, which will basically separate out these particles by mass, hence the name mass spec. And it will come off on sort of a sheet, if you will, or a printout, and they will come off at different times, and you'll have some different peaks that will essentially come off. And that is how they kind of separate them out by mass. They also can measure the peaks that they see on the graphs, and they can determine sort of the percentage of each of those isotopes that basically come off. So this is sort of what one looks like a little bit here. As they send it through, the 37 chlorine isotope will come off differently because it's heavier, for example, than the chlorine 35. You can see here that the 35 chlorine there is 75-ish, and bad straight line, but 25-ish there for our other guy, about 100% in terms of relative abundance. So you get these different sort of size peaks that come off in this process. And again, it basically will be able to kind of separate it out by size as it goes through this sort of system here. So you send your sample in, you basically heat it up really good and ionizes it. It goes through an electrical field. Remember, electrical field will be able to bend, if you will, charge particles as they go through. Magnetic field will do sort of the same idea, and it'll come out here on sort of the detector and then onto your graph, obviously. And you can see kind of your lightest particles will come off there first, and then your heavier guys there on one side versus the other. And again, by analyzing the peaks, they're able to determine the percentages of each of those isotopes to come off. And also how many different isotopes basically would be there through a sample as well, based on obviously how many different peaks that you have coming off in your sample. All right, so why don't you try one here? If copper is 69.1% copper 63, and it has a mass of 62.9396 AMU, and the rest of it is copper 65 with a mass of 64.9278 AMU. What is copper's atomic mass? So why don't you take a moment there and calculate. Okay, so let's take a look. So obviously we got a couple of isotopes here. So we got copper 63. That is occurring 69.17% of the time and has a mass there of 62.9396 AMU. We have another isotope here of copper 65. Does not give us our percentage, but does give us the mass 64.9278 AMU. Here we do need to figure out, right, our sort of missing percentage. And we know that under the assumption here that these are perhaps our two naturally occurring isotopes, we know that they should add up to 100%, right, if we had everything. So if we take 100% and minus 69.17%, which is the percentage of the first isotope there, we will get the percentage of our kind of second isotope, which in this case is 3083%. Obviously, that would be our missing sort of percentage. So sometimes you may need to do that. Obviously, you want to assume 100 and subtract off. Now that we do have the percentages and the atomic masses of each isotope, we could do our calculation. So our atomic mass in AMU here will be our first isotope. I'm just going to move the decimal point on it, which means it's going to be 0.6917. Again, you could divide by 100% if you like to have it do it for you. We're going to times it by the atomic mass there of our first isotope. We're going again here to add, not multiply. So we're going to add now the second isotope. And again, if you don't want to move the decimal, you can just divide it by 100% and it'll do it for you. And we're going to multiply that by 64.9278 AMU. And here we will get there 6355, I believe, for the atomic mass there of copper. And that is what you actually do see if you take a peek there on the periodic table. That would be the number that you see underneath it. Any questions on that calculation there? Hopefully they agree. Let's see. They do. So that's good. All right. So now that we talked about atomic mass, we're really going to kind of talk about using that number in a different way. But before we do that, there is obviously words that we have in life that does represent a certain amount of something. So when you say you have a dozen of something, like eggs, for example, that means you have 12. When you have a pair of something, that usually means that you have two. And if you have a gross of something, that's how much? 144, in case Jeopardy question ever comes up. 144 on the gross there. Very popular years ago because they just gave out pencils and grosses. So you get a gross of pencils. Now, in chemistry, we actually do have obviously a number or a name that represents a certain amount of something, and that is our friend the mole. And the mole is not the furry guy, it is the mole here. And it does have an abbreviation, and they had to cut something off, so they did cut the E off, and that is MOL, which unfortunately for a lot of people gets them in trouble because a lot of people, when they see MOL, they automatically jump to molecules and they think in their head molecules for that. So that is the abbreviation for moles. It is not molecules. Trust me when I tell you, if they want molecules in a problem, they will write out the word molecules for you so you don't have any misunderstanding. So again, MOL is the abbreviation for a mole. So 1 mole of something equals 6.022 times 10 to the 23. And the units associated with that number, which by the way is our friend not avocado, Avogadro's. Avogadro's. I almost wrote avocado. Avogadro's number there. The units associated with that is it could be particles, could be atoms, could be molecules, could be pizzas, right? Could be shoes, perhaps. So outside probably of the occasional pizza question, I'm probably thinking in chemistry, atoms and molecules are probably going to be your most common unit there of Avogadro's number. It does again sort of change based on sort of the problem that you're doing. So a mole represents basically as many elementary entities as there are in 12 grams of our carbon-12 isotope. So what is sort of Avogadro's number used for? It really is a conversion factor. So Avogadro's number is really used as a conversion factor. It is the conversion factor that allows you to go from moles to either atoms or molecules, depending on what you're doing, and backwards. So that right there is our conversion factor. Avogadro's number to do that. Now, the problem with Avogadro's number is people learn Avogadro's number and they decide they should use it in every calculation they do, which is definitely not the right idea either. So the idea here is there should be some keywords that tells you I should probably use Avogadro's number in this situation. And really those two keywords in most chemistry cases is either you are given a number that's in atoms or molecules, or you're asked to solve for something that's in atoms or molecules. If you're not given any of that, you should just leave Avogadro's number on the side where it usually stays most of the time outside of the chapter it's in a textbook. You don't need to use Avogadro's number unless you see any of those sort of words. So we do use it as a conversion factor. And again, basically here, we could go 6.022 times 10 to the 23 atoms or molecules over 1 mole. Or we could flip it around and put the mole up on top and use 6.022 times 10 to the 23 atoms or molecules on the bottom. So if I have something like 1 mole of hydrogen, it has 6.022 times 10 to the 23 atoms of hydrogen. Again, that gives us basically two conversion factors, the Avogadro's number over 1 mole, or 1 mole over 6.022 times 10 to 23. Now, if I had 1 mole of water, I would have 6.022 times 10 to the 23, and these would now be molecules of water, as water is a molecule. So again, the units of Avogadro's number can change, and it is based on sort of what you're using it for. But again, atoms and molecules are basically your two common ones. Any questions on that there? Now, like I said before, although atomic mass is a unit that we get from the periodic table, honestly, the most used sort of conversion factor that you get from the periodic table is actually molar mass. And the units of molar mass are grams per mole. And the number should always stay with the grams part, and it should always be 1 mole of something. And we get the molar mass from the exact same place we get the atomic mass. We get it from the periodic table. It is that number on the bottom, and that is the molar mass, in addition to be the atomic mass of these things. And what that means is if I have 1 mole of hydrogen, hydrogen has 1.008 grams, basically. The molar mass of hydrogen, 1.008 grams per mole. And we can use it as a conversion factor. And molar mass is our conversion factor to go from grams to moles and moles back to grams. Probably the most two common calculations that you do in chemistry, grams to moles, moles to grams, using the molar mass is probably more so than you will ever see Avogadro's number used in real life chemistry situations. So definitely something that we use. We get it from the periodic table. And again, we could use it as a conversion factor. So 1.008 grams of hydrogen over 1 mole. Or again, you could flip it around if you need to. 1 mole of hydrogen would be 1.008 grams. Now, we could also obviously get the molar mass from things that are molecules. So if we had water, we basically just add up all the parts from the periodic table. So we go to periodic table, each hydrogen is 1.008 grams per mole. And if we go to periodic table, oxygen is 16 grams per mole. And if we add that together, that gives us the molar mass of water as 18.02 grams per mole. Also can be used as a conversion factor to go from grams to moles in that particular situation. Now, numerically speaking, the atomic mass that you see on the periodic table in AMU per atom and the molar mass that you see on the periodic table in grams per mole are numerically the same values. So they come out the exact same. So There is a conversion that involves Avogadro's number, but basically AMU and molar mass in grams are essentially the same number. So that's why we can pull it off. Also, when we do pull off the molar mass from the periodic table, once again, that is 4 significant figures that we typically take off the periodic table, and it will vary on the periodic table you're looking at as to how many numbers you might see underneath there. Any questions on that there? So how are all these related to each other? Well, obviously here, if I have 1 mole of hydrogen, that will equal 6.022 times 10 to the 23 atoms of hydrogen. And 1 mole of hydrogen will equal 1.008 grams, basically. If I have 1 mole of water, that will equal 6.022 times 10 to the 23 molecules of water, and that would equal 18.02 grams of water. So when we go from grams to moles to atoms, if you will, are molecules. We would need the molar mass heading in this direction, and then we would need Avogadro's number to go that way. And obviously, if we're heading backwards, we would need the same 2 things, Avogadro's number and then molar mass. We could see that the thing that ties grams and atoms of molecules together, that is our halfway point between those two. It is moles that basically ties those guys together. And again, those are some common sort of conversions that we do. Any questions on that? Now, a really important thing about molar mass that people oftentimes screw up right around the time we get into stoichiometry and we're balancing equations and stuff like that. So let's just say we had an equation and we had to do some type of calculation from it, and we needed the molar mass of water. Should I include the 6 in my molar mass of water? The answer is no, you should not. So the coefficient in the balance equation does not affect the molar mass. When you're asked to calculate the molar mass, the units of molar mass are grams per 1 mole. And that means that you should always calculate the molar mass as something based solely on the formula by itself, regardless, for example, in a balance equation, if it has a coefficient in front of it. You take into account that coefficient when we talk about stoichiometry and later calculations, but always molar mass, you just take the formula by itself, one of them, and that is how you should always calculate the mass. And that's really the definition of molar mass. It is, again, per 1 mole, and this would represent 1 mole of water here. This would represent 6 moles of water. So again, molar mass is per 1 mole, and that's how you want to calculate it. Any questions on that there? So let's try some here, maybe. Here's 1 mole of each of these substances. And again, if I did put, say, 1 mole of all these guys into beakers, would they all look visually the same amount? They wouldn't, right? Because 1 mole carbon is 12.01, right? 1 mole of sulfur is 3207 grams. So although they all represent 1 mole of something, sort of physically, if you will, in terms of grams, they do represent a different amount of grams in each of those cases. All right, so just some conversions here and relationships of all 3 of these things. Again, our AMU to gram conversion, and you can see that essentially there's Avogadro's number, which is why the AMU per atom and grams per mole basically are going to be the same number. All right, so there's our conversion there along the way. All right, so why don't you calculate the number of grams there are in 15.7 moles of iron. In case you don't have your periodic table, look at iron. We got 5585 happening there. Okay, so let's take a look. So first off, we want to think about, do we need Avogadro's number here? Do I need it? I do not need it. Again, I'm looking for grams. I have moles, no mention of atoms or molecules, so no need for that. This is going to be basically a moles to grams conversion, which is the molar mass from the periodic table. That's going to allow us to do that. That gives us our molar mass here for iron of 5585 grams per mole. You could also flip it around and use it in the other way. So we're just going to take a dimensional analysis approach here, 15.7 moles of iron. We want to go opposites to cancel, so we do need to use it in this form where the moles are on the bottom and the grams are on top. Again, the moles will cancel, and so maybe an 876.845 grams. Sig fig wise, probably looking at this number right there with about 3 of them. And I'll call it 877 grams of iron. Any questions on that one there? Yeah. Again, super common conversion, moles to grams and also grams to moles here. All right, let's take a look at maybe a few more here. Let's do our friend lithium here. Lithium, I think, is 6.941. I think there on the periodic table. Here, we're looking for moles. We have grams, so we're doing a grams to mole conversion. No Avogadro's number needed. So again, the molar mass is our conversion. We go to the periodic table, 6.941 grams per mole is the molar mass here. Also could flip it around if necessary. So here, starting with our 77.8 grams of lithium, in this case, we want grams on the bottom, so we are going to need to flip it and go opposite there so that they cancel. Per mole of lithium, grams will cancel, so we're essentially dividing by what's on the bottom, right? So 77.8 divided by 6.941 will go 11.2 moles of lithium in this case. Also, 3 sig figs probably based off of the first number there in the calculation. Any questions on that there? All right, so we want to know how many atoms are there in 0.551 grams of potassium. All right, so here we are looking for atoms, which is a pretty key word. That means I should probably need to use Avogadro's number somewhere along the way there. So we will need to use our 1 mole is equal to 6.022 times 10 to the 23 atoms in this case. We are starting with grams, and we do want to get to atoms. And remember, as we just talked about, what kind of ties both of those things together in the middle there is moles. So again, we need to kind of go grams to moles using the molar mass from the periodic table. Once we have it in moles, that is the point where we could then use Avogadro's number to kind of finish the whole journey there. So once again here, molar mass for potassium, 3910 grams per mole. We're going to use that as a conversion factor, so 0.551 grams of potassium. Opposites to cancel, so we're going to go grams on the bottom, 3910 grams per mole of potassium. If I stop the calculation right at this point, I am in moles of potassium, which you could get an answer, but you don't necessarily have to since we want to go all the way to atoms. So we could continue on with the calculation. Again, as we talked about a number of times, the benefit of setting this up in dimensional analysis, besides that is the way you're supposed to show your work, is we could clearly see at this point that moles are up on top. That means, again, to cancel them when we use our Avogadro's number here, we do have to put the moles on the bottom, and Avogadro's number should go up on top. That way the moles on top and the moles on the bottom will cancel. At this point, we have only atoms left over on top, which is good. We're going to multiply whatever we got going on top. We're going to come back and divide by whatever we got going on there on the bottom. And if we do all that good stuff there, 0.551 times 6.022 to 23, divided by 3910. That's going to get us here 8.49 times 10 to the 21 atoms of potassium. Any question on that step there? You obviously could get an answer there for the first step. Again, I would probably not round too much until you kind of do the second step there. Any question on those calculations? All right, let's take a look at a few more here. Actually, we're going to skip through these, kind of similar we just did. All right, so let's try this one. How many hydrogen atoms are there in this? Actually, we'll come. Let's actually do this one first and we'll come back to that one. So let's do this one here. How many moles are there in 23.2 grams of ethanol? And how many molecules are there in 23.2 grams of ethanol? Some information here. Carbon 12.01, hydrogen 1.008, and oxygen 16. All right, take a few moments there and calculate that up. Okay, so let's take a look at this one here. First one, we want how many moles there are in that many grams. So this is, again, a grams to moles conversion. That is the molar mass from the periodic table. Here we just need to add up all the parts. So we do have 2 carbons, each at 12.01. We have 6 hydrogens. That's what I think it says. 1.008 grams per mole from the periodic table for our hydrogens. And lastly, we have just 1 oxygen, which would be 16 grams per mole from the periodic table. That's going to give us a molar mass of this compound of, I'll go 4607, I think, grams per mole. So again, that is going to be our conversion factor here. So we'll go 23.2 grams of our ethanol here. We're going to go opposites to cancel. Grams are on top, so we do need to put the grams on the bottom and our moles up on top. Grams will cancel, and we will end up with here 20, what we got there? 23.2 divided by 4607, I believe, will get us 0.50. I am going to round since we do want this as one of our answers here, moles of C2H6O. Any questions on that part there? Now, at this point, for the second part, we really just want molecules, and that tells us Avogadro's number needs to be in play, and that is 1 mole is equal to our 6.022 times 10 to the 23. Here we will use molecules as a unit because ethanol is a molecule. We really could just honestly pick up from here, and we'll go 0.504 moles of C2H6O. We're going to go opposites to cancel, so moles on the bottom, Avogadro's number up there on top. Clearly, we want to make sure we're using our exponent button when we do this. Moles will cancel. Also, I'm going to use the entire number that's on my calculator, not the rounded number, when I multiply it, 6.022 to the 23. And that's going to give me here 3.03 times 10 to the 23. Molecules of our ethanol in this case. Question on either of those calculations there. All right, we're going to lay it up there for